Alright guys, let's look at an example of something called eliminating the parameter. So what does it mean to eliminate the parameter? So in these parametric equations, t is the parameter because x depends on t and y also depends on t. So the parameter being t is eliminated if we get a new equation that only contains y having to do with x, or vice versa, x having to do with y. So the way we're going to do this is we are going to solve one of these two equations for t, and since it shows up in the other equation, we'll substitute and replace it with t. So of these two equations, I can see this one's got a radical around the t minus 1, which is in the denominator. This one doesn't have the radical. So of the two equations, this one looks like it's going to be an easier one to solve for t. So how would I do that? Well, the first thing I'm going to do is start with this, and I'm going to isolate the t minus 1. So notice if I swap, this is I've got a fraction, this doesn't. If I want to get this out of the denominator, multiply, and then I would divide. So what ends up happening is I just kind of switch places with these two. So I end up with t minus 1 where the y was, and y down there where the t minus 1 was. Okay, and it's simply just multiplying both sides by t minus 1, dividing both sides by y. I would get this equation. And then what am I trying to do? Remember, I'm trying to get t isolated, so I need to add that 1 over, and I would end up with this. T equals 1 over y plus 1, just adding that 1 over to the other side. So this is what I'm going to take, and I'm going to substitute this into the other equation that I didn't use. I used this one, so I didn't use this one. Well, where that t is, I'm going to substitute all of that stuff that t is equal to. All right, there's t. I'm going to replace all this stuff in place of that t. And then if you look what's going to happen, I'm going to have 1 divided by the square root of 1 over y plus 1 minus 1, meaning there's not going to be a t. And I have eliminated the parameter. All right, t is the parameter. That's how we eliminate the parameter. All right, so there is the 1 over y plus 1 in place of the t, again from the last slide. So I'm putting that value in there where that t was. And now it just becomes an act of simplifying. So the first thing, if you see what's going to happen here, is I'm going to cancel these 1's out, like so. That's going to leave me with 1 divided by 1 over y underneath the square root plus 1. So these canceled, so I just have this with the 1's gone. Okay. Now, what we have to remember here, this is a little simplification step. This is going to end up being just the square root of y plus 1. Now, how did I get that? Well, this on the bottom, this becomes 1 over, I'm going to write it as, because it's the square root of a fraction, I can do the square root of the bottom, the square root of the top on their own. Right? And then the square root of 1 is 1. So this becomes 1. This is my overall division bar, right, before we did the substitution. So this is 1 divided by this fraction. And how do you divide by a fraction? Remember, you flip and multiply by the reciprocal of the fraction. So I end up with 1 over the square root of, I'm going to put that plus 1 in there, 1 times the square root of y over 1 plus 1. And these 1's are not going to do anything. I'll just get the square root of y plus 1, which is what we got for our answer. So what does that mean? That means our original parametric equation and what we got when we eliminated the parameter should give us the same graph. So recall our original parametric equation was x was 1 divided by the square root of t minus 1, and then there was a plus 1 right there. All right, so that's x. We don't, when we're doing parametric with Desmos, remember we don't have to write x equals this, y equals this. We're using point notation. This is the x coordinate, x comma y. So this is how we get x, doing that to the parameter. And how did we get y? We divided 1 by t minus 1. All right, now look, we don't see anything. Why don't we see anything? Because notice the default with Desmos again is to do the parameter between 0 and 1. Well, if I plug in 0, I get the square root of -1. All right, if I plug in 1, I get 1 minus 1 in both of these denominators, which is 0. Square root of 0 or divided by 0. So we have to be bigger than 1. This says less than or equal to. Technically, it has to be 1 is strictly less than t, but we can't change that with Desmos. And then just make this some bigger number. This is going to be making its way. The closer and closer we go out, this thing is making its way towards 1, 1, 0. And you can see that if you plug in a big number here, we get the square root of a big number. 1 divided by a big number is 0. 0 plus 1 would be 1. And then over here, we would do the same thing. A really big number minus 1 as we make our way to infinity. A really big number minus 1 is still a really big number. 1 divided by a big number is close to 0. So we end up really close to the point 1, 0 as t gets bigger and bigger and bigger. So the closer you get to infinity, you can start to see that that thing starts to get smaller and smaller and smaller. All right, so anyway, our closer and closer to 1, 0, that is, I should say. All right, and then what did we get when we eliminated the parameter? We got x was equal to the square root of y plus 1. And there they line up right on top of one another. So that's a way you can use Desmos to check, did you eliminate the parameter correctly? Here was the parametric version, x equals this, y equals this, and then here's what I got when I eliminated the parameter. And they're right on top of one another. All right, what if I have trigonometric functions in these parametric equations? So I have x equals 5 cosine theta, y equals 5 sine theta. Well, if you recall, x equals cosine and y equals sine, that is the equation. X equals r cosine theta, y equals r sine theta. That is the way that we convert between r and theta and x and y when we're going from polar to rectangular. So this is actually just describing a circle. So what I do in that case, when I see cosine and sine in there, it's very common to square these values for x. So x equals 5 cosine theta, y equals 5 sine theta. If I square those, I get x squared is 5 squared, which is 25, cosine theta squared, which is cosine squared theta, and then y squared would be 5 squared, 25, sine squared theta. Now, because I have a cosine squared and a sine squared, I can add these together, and I get x squared plus y squared equals 25 cosine squared plus 25 sine squared plus 25, and like we've seen before, cosine squared plus sine squared is equal to 1, so 25 times 1, and we get x squared plus y squared equals 25, which is a circle centered at the origin with radius 5. So it's very common when we have these parametric equations that involve sines and cosines. It's very common to say, if it's x equals something to do with cosine, y equals something to do with sine, to square those values for x and y and then just add them together to get that sine squared plus cosine squared equation to produce a 1 and help us get rid of the parameter that way. That's still, if you look, our parameter here was theta, and by squaring, combining this together, we went from these all had theta in them to now there is no theta. So we just have equations with x and y and no parameter left. So that's another way to eliminate the parameter when trigonometric functions are involved. All right, and then finally, if we are told, we're given a rectangular equation and we're told to come up with a parametric description of that, the easiest thing to do is to look at this and come up with dependency. Like who depends on who? And it's easy to see here y depends on x because y is isolated, y is solved for. So in that case, we are being told how to get y if we know x. Okay, but we're not we don't have x isolated. So in that case, the easiest thing to do is to make x equal the parameter directly, and then let y just be equal to instead of x squared, make it be equal to the parameter squared plus 3. And then we get a parametric representation of that graph with a very straightforward way to do it. Okay, so again, how did I pick it? Y dependent upon x. Y was isolated, so I let the other variable be equal to the parameter, and then I just replace the variable I let be equal to the parameter with the parameter in the equation, and then I get that. Okay, now we could also, if I had, if I plot this, my original function was y is equal to x squared plus 3. So that's just a parabola that opens upward, shifted up 3 units. And then my parametric representation was t for x, and just replacing x with that parameter for y. Okay. Now, notice we only get this tiny little snippet, so t would have to be able to vary between, a lot of different values for this to work. We'd have to extend this out into the negatives to make it to cover it for all that we can see here. But remember, I don't like this version of Desmos because I can't see the movement within the curve. That's the big benefit of coming up with a parametric representation, is to come up with how the value changes within the curve. So I like to use A for again another version of the parametric equation, and then I plot it again with A as the parameter instead of t. So A and A squared plus 3. And then when I do this, I can then move the parameter around and see how the graph changes. So and I always like to use this double forward, as time moves forward, as the parameter grows, we move left to right. So there's our left to right motion with the parameter. Now, if we wanted to reverse that, obviously we can't just do what we just did here, just make t the parameter and move that way. So if I wanted to move, for instance, right to left, what I'd have to do is I'd pick a starting point. So let's say I had -5 to 5. I'm going to pick, instead of -5 to 5, I'm going to pick 0. I'll say b equals 0. I always just switch this to 0 and go the same distance. -5 to 5 is 10 units. But start at 0. And then what I can do is I can make this be some value like 5 minus the parameter. So when I subtract 0, the low end, from 5, 5 minus 0 is 5. I'm over here. And then when I subtract the upper end, 5 minus 10 is -5. I'd be over here. Okay, so that's a way I can do that. And then comma, this is x. How do I get y? I square x and add 3. So I square 5 minus b, and then I add 3. All right, and now I can move forward on that. See, now I'm on the curve, and I'm moving in opposite directions. Okay. So anyway, that is a way that we can plot this and change direction on it. If we need to come up with a parametric representation of a graph, that's a way to do it.